In this video, we're going to be talking about how to write equations from parent functions and transformational descriptions. We're really just going to be focusing on two different functions, the quadratic or your x squared function and your absolute value function. And we'll talk about how it moves and changes on different transformations. So first we need to remember or look at what a quadratic function looks like. So I'm really just going to pull that information from the table. So I'm going to put that in my calculator and actually from this one on, I'm going to do equations. I put this in my calculator, equals x squared, go into my table. I can graph a bunch of these points. I know it's a little small, but you'll still do this. So this graph goes up to 6, so I can do -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And then make my worksheet do that. So this would be our quadratic function if we didn't move it, stretch it, flip it, none of those things. It would just be this. Now we're going to talk about what happens every single time we change something. So I'm going to keep this in. This is going to be my parent function. How everything else moves is in relation to this one. And I'm just going to put in the next line. So x squared plus 2. Plus 2. And it's going to graph both. Now, online, I'll be able to see it in color, so I'll be able to see which one is different. But let's say these were the same color. If I wanted to see which one is different, then I could go to this, and you have the same function on your calculator. Go to this and change the type of line so that it's thicker. So when I graph it, I have a thicker line and I have a thinner line. The thinner line is what I'm comparing to the thicker line to. And I'm looking and seeing what happened for change. And when you write these changes and these rules, you should be able to write it as if you were explaining it to someone who's not here. So when you look at this, the thinner line moves up. The rule for that would be, and these are fancy words, that it translated to units. So then you can probably think about what would happen if we moved it down to, but let's see. Now I'm going to take that same equation that was plus 2, and I'm going to change this to minus 2. And as I said, the original, the parent function, is now moved down to. So that would be translated 2 units down. Now we're going to see what happens if we have parentheses and what this does. So I'm going to go back into my y equals, and I'm going to clear this out and put in parentheses. And square it. So that's my original, and it looks like my original moved to the left. If you think back to our vertex and finding that, usually we took that inside number and we changed it and made it the opposite of what it actually did. That same thing applies here. Even though it said plus 2, it really did the opposite. So instead of moving to the right 2, it moved to the left 2. So this would be another translation. But this would be moving 2 units to the left. So then, of course, you can probably guess what happens if we have minus 2. It should do the opposite, but let's double check. Now, instead of plus 2, we're moving this. And as I said, it did just that. So this moved right 2. That would be translated 2 units to the right. Now we're going to see what happens if we do 2 times our parent function. We're going to figure this out, put 2x squared. And you can probably start to guess what might happen, but let's see. So as you're looking at the original, our parent function, and then you're looking at that 2x squared, it looks thinner, short. I think most of this work. What it's really doing is stretching. So I'm doing this, but you can't see it. It's stretching the quadratic along the y-axis so that it's vertically getting bigger. So if you were to describe this, we can say narrow. But the actual rule would be stretched vertically by a scale of 2. Then if we put in 1/2, you can probably think about what's going to happen. So we're going to delete that and insert 1/2. And now So now it looks like it's gotten wider, and what it's really doing is it's compressing or shrinking away from the y-axis. So the rule there would be compress vertically by a scale of 1/2. So we talked about translating, we talked about stretching and compressing by a scale. The next thing is what happens if we have a negative output. So I'm going to go over equals, I'm going to make this negative. So negative x squared. We can probably already think about what happens when it's negative, because we talked about if your a value is positive or it's negative, what happens. So if I graph this, I have my parent function, and then I have the negative version of that. It literally is flipped upside down. So if we have a negative outside of the x squared, this would reflect. So, and a lot of these words we should remember from geometry, but this reflects over the x-axis. Think about it like it was a top, it would be here in between them, and also the bottom. Now we're going to take all of those different types of transformations and apply more than one. So now we have a negative and a plus one. You can probably start thinking what would happen. You're going to be taking what you saw before and combining them. So I'm going to go ahead and do that. Negative x plus 1 squared. So there's my original. So it looks like it's been flipped upside down, and it's been moved to the left one. And that's exactly what happened. I'm putting quotations and so you take both of those rules and make this bigger into words and not I'm going to do that. So that would mean it reflected over the x-axis and it translated, which one unit. As you start to get more and more comfortable with this, you should be able to look at it and say exactly what happened without really seeing it visually, but we'll do that really fast. And then on the back, we'll do a couple, but then do the rest without really looking at it. So I put in the x squared minus 2. Again, you can probably sort of guess what happens, but if I graph it. So from my parent function, it's gotten narrower, and it looks like it was moved down So narrow and down 2. So then to put both of those rules, I would say the narrow, if I go back, whenever it got narrow, that was a stretch vertically by a scale of whatever it was. So this would be a stretch vertically by a scale of 3. And then down 2 would be a translate down 2. Doing this last one. Now we have negative 1/3 x minus 3 squared plus 1. You'll probably be thinking, I'm doing a lot here. A lot of things are happening, and that would be correct. Yes, we can go ahead and put this in. So we have negative 1/3, and then in parentheses, x minus 3 squared plus 1. So take these in one thing at a time. This got wider. It was flipped upside down. It was moved to the right. And it was moved up. Now, I've been doing this a lot, so I can easily say all of those things, but let's say you're not seeing those things. I'm going to kind of draw. Think about this point right here. Think about where it is now. It's now right here. So it was definitely moved to the right and moved up. Then, if I'm thinking about how this looks, this is definitely wider, and it's clearly upside down. So do that if it helps. So there's going to be a bunch of things that happen. So this was got wider. It moved right, and moved up. Putting those all together, ignore how sloppy that looks. This, when flipped, it would be reflect over the x-axis. For wider, would be compressed vertically by a scale of 1/3. For right 3 would be a translate movement to the right. And then move up 1 would be another translate 1 movement. Now, we are going to talk about absolute value. So again, I'm going to put that in the graph. Absolute value, there's a couple of ways to get to this. The easiest is this. And the first one, you put an S, and then going through the equation, and figure out this twice. What you see is that all these values are the same, so grab as many as possible. So it's at negative 6, 6, negative 5, 5, negative 4, 4, and you see this until it gets to 0. And then at 0, it's going to go back up, so 1, 1, 2, 2, and all those. We're going to do the same thing we were just doing, look at some of these changes. Again, as we look through some of them, we'll be able to guess because they'll be the same as before. They're not going to change just because it's a different function. This is a little different. So this will be my parent function of my absolute value. I'm going to take that and add 2 on the outside. So if I subtract that, I have my original, and then I have my plus 2. So then I'm going to go back and do all the rules here in a second. So if these start to look the same, now let's move down to, and without really looking at these, I could finish this. Now again, you could still go back and put this in your calculator. You have that at home. You can use Desmos to see that change also. So I'm going to write all of the changes. So this would still be, I said move to, but there's this move to up, move to down, move to the left, move to the right. The 2 tiers on the outside, if you're not sure, you can just put that back in. And see that it's doing the same thing it did for the quadratic, which is a narrow. Which means this y. Here is where it's a little different. We have negative on the outside. So that still does what we did before. Flip it upside down. But the other one is on the inside. Do that, it doesn't look like anything else. So I'm going to go into the body, and I'm going to change the color. And you can kind of see that that red line is lying on top of the blue line. So the change is nothing, but there is a different rule. So we'll fill in the rest of the rules and then we'll come back to that. So if all of the changes are the same, this would be translate to up, translate to down, translate to the left, translate 2 units to the right, narrow would be a stretch vertically by a scale of 2. Okay, wider would be a compressed vertically. By a scale of 1/2. Flip upside down would still be a reflect over the x-axis. The negative x still did something, but what it actually did was reflect over the y-axis. So you're probably wondering, how do you see that? We're going to talk about that here in a second, but imagine that there's a mirror on your y-axis, and you're flipping it over that. It would fall into this. Which is why the change was really nothing. We'll talk about why that is here in a second. Alright, so now that we've put a bunch in the calculator, we're going to try to do this without the calculator, and then we'll double check it. So if we are multiplying by a fraction out front, in the past when we've multiplied by a fraction, it's gotten wider. And we're also adding 5 to the entire function. So in the past when we've done that, it's moved up up 5. Moved up, but 5. And then the rule for those would be compress vertically by a scale 0.25 would be by a scale of 1/4. Moved up 5 would be a translate up 5 units. Right, now to test that, to see if it did those two things, I'm going to put my parent function back and that and see what happens. So I had this in here, but I changed some of the settings. So let's go back. I think this is actually thick. And we'll change this to a thinner line, but I'll keep the color red. So this would be my alpha window, absolute value of x, so that's my parent function. And then I have 0.25 alpha window, absolute value of x, and then plus 5. And then I'm going to graph it. So there's my original. So it definitely got wider, and it's definitely been moved up 5. So those. So once you start to get the hang of this, you may not need to actually put it in your calculator each time. For the next one, we have a negative on the outside. So in the past, that would have been flipped upside down. And then we have -7 on the inside, so that would have been a moved left, moved right 7. And here's where maybe you don't remember, is it moved right, is it moved left, I don't remember, because the negative is throwing me off. Then you can put whatever you think the rule is, put whatever you think the change is, put it in your calculator and double check yourself. So I'm going to put my rules that relate to this. So this would be a reflect over x-axis and translate 7 units to the right. So when I put that in, let's see what happens. Go back to my white equals, clear the second one out, put negative alpha window, my x, and on the inside I need -7, and then on the graph, so there's my original. It was definitely flipped upside down, and I could see it was moved to the right, so what I put was correct. Right, for this last one, you really have to think about, okay, what happens when I have all these things? So if I have a number that's not a fraction, then it usually gets narrower. +2 on the inside would be moved left 2, and -1 on the outside would be moved down 1. So those rules would be stretch vertically by scale of 5. Translate 2 units to the left, and translate 1 down the unit. And I could graph that just to make sure. So if I go down and I clear this out, I have 5 times the absolute value of x plus 2 minus 1. And I graph it, minus 1. There we go. So it's definitely gotten narrower. It's moved to the left 2. And it doesn't look like it, but let's say I trace this. Oh, I'm going to trace again. Let's go to the other one. There we go. Ooh. If I were to find like the lowest point, it would be a -1. It just doesn't look like that right at this moment. All right. Now, earlier I talked about how if we have a negative on the inside, we don't really see that change, but we did see like with the 2 different colors. So why that is if we want to see an actual reflection of the y-axis, we have to move our graph left or right first. So if we have this function, f of x equals absolute value of x minus 2, where we're translating the graph 2 units to the right, and then we have a negative on the outside, so we should already know that this would be flipped upside down. Because this would be a reflection or reflect over the x-axis. But if I put in this bottom one, so absolute value of negative x minus 2, and I graph it, it kind of throws you off a bit because it said minus, but it's still to the left. And it really looks like it was shifted left 2, but it doesn't say plus 2. So with this, it's a little weird because we have to think about this like this. When you have a negative on the inside and those other things, we could like factor out that negative. I know it's been a minute since we've done some factoring, but I could rewrite this as x plus 2. Now I'm going to put this in a different color. Let's say pink, sure. And I'm going to put in negative and then in parentheses x plus 2. And actually, let's not make this pink. Let's make this some other color that we'll be able to see really nicely. Sure, green. And then I'm going to make this line thick. Okay. So now when I graph this, I have my parent function. Oh, I must have also had green mystic. Okay, try again. Parent function, I had that original function that we got, and the one that I just created, and notice how it graphs over top of this. So what does that really mean? Is it that I moved to the left 2, or did I move to the right 2? And it was reflected. Kind of both. They you could say either or happened because it would give you the same graph. So if we're going with this one, this would be I'm sorry, and I forgot one. This should also be moved right 2, sorry. Space there. Anyway, so I could say based on this one, this should be what did I say? Sorry. That there was really no change except for moved left 2, or that it was flipped over the y-axis, which the rule will kind of match that, and moved left 2. So with these type of problems, it gets tricky because then you're like, okay, but which one is right? Both, really? For a lot of these problems, there isn't just one way you can find the same problem, and that's not encouraging, I know, but both are technically right. So this, however, would be a reflect over y-axis, translate 2 units to the left. So now you're probably thinking, okay, what happens if I get that? It depends on what the question is asking. I would say if it's asking to write the transformations, you see that there's a negative here. So there should be some sort of flip, reflection, something. If you want to rewrite it so that you actually know what those 2 things are, you could do that. But you have to be able to write both. All right. We're going to talk about just some general things and then do a couple of these practice problems and then be done with this video because I know it's pretty lengthy. Okay, so vertical. There are a couple things you need to know about vertical. One, let's talk just about shifts. I'm going to draw in all of my, actually, because translated is going to be shifts. That's okay. You'll see why there's so many things here in a second. So for vertical, for anything vertical, this is affecting the y values. So you can say the horizontal is then affecting x values. For vertical, I can move this up or I can move this down. For horizontal, I can move this to the left or I can move this to the right. And I'm just using quadratics just because it's the easiest. I could have easily used absolute value as well. So for translated, that's when we are shifting things or moving things. Notice when we translate or shift, we're moving up and down, left and right. There is no diagonal things going on. So we can move up or down, or vertical, which we kind of just did, or left and right, or horizontal. Okay. For reflected. For reflected vertically, this is going to flip it completely upside down. I should actually draw in the parent function for everything. It's not a good parent function, but sure. So if this is the original, reflected vertically would be upside down. Horizontally would overlap this because we can't really see the horizontal unless it's moved because we're really taking it and going around the y-axis. Stretch vertically. Do all of our parent functions. So stretch vertically would be it getting narrower. It's stretching towards the y-axis. Your y values are getting bigger. Stretch horizontally is stretching out towards your x-axis because your x's are getting bigger. Compress vertically is stretching out away from your y-axis. I know stretched horizontally and vertically compressed look the same, which in reality they really are. But if we are vertically compressing, we are shrinking away from the y-axis. Horizontally stretching, we are stretching towards the x-axis. So for a horizontal compress, we would be stretching, or I'm sorry, not stretching, we would be shrinking away from the x-axis. So that would also look similar to the vertical stretch. Right. So now that we have all of that information, we're just going to do a couple of these. Let's do, there's 4. We'll do a scale one. And we can do these all real fast. Okay, if x squared is translated 4 units down, so if you need to think back, okay, if I'm moving something down, that's a vertical shift that's affecting my y's, and that's going to be outside. I should also go back and do that. Outside, inside. Usually if we have a horizontal something, it's inside the parentheses or absolute value or inside the function. If we have a vertical something, it's outside of the function. So this would be outside, and we would be subtracting 4. 2 units to the right would be inside, and right is usually minus, so that would be minus 2. So then this would look something like this. F of x equals, we have inside x, the negative 2, we're going to have x minus 2 squared, and then outside we would have minus 4. You could graph that and make sure it looks okay, but I promise you it will. Right? Next one, we have if f of x is x squared equals x squared, it's reflected over the x-axis. So even though we said that the y values, or the vertical, the vertical affects the y values, and the horizontal affects the x values, think about what happens. Which one reflects over the x-axis? So let's go back to our pictures. We reflect over the x-axis. That means we're doing this. And that would be a vertical reflection. So that would be outside. Then we have translated 7 units to the left. That's going to be inside. To the left is usually a plus, so that's going to be a plus 7. So when we write this, it's going to be f of x equals, on the inside we have x plus 7 squared. And then, I forgot about this on the outside. Because it is reflected over the x-axis, we need this negative on the outside. Those numbers are usually out in front. We could also go back and start putting in some of these things. So a vertical is going to be a plus, you can say k minus k. Horizontal is going to be a plus h minus h, if it's in the form, some vertex form for quadratics or absolute value. I'll just write it. So then reflected would be A is -1. Actually, I think there's another letter because I think there's something here too. Maybe it's a B. Sure, let's say it's a B. But a horizontal reflection would be B equals -1. A stretch would be A is greater than 1, so it'd be some whole number. For horizontal, that would be a B. We're not going to talk about that B right now. It gets a little bit confusing, so just know it's the B value. The compressed would be the A, and this would be less than 1, it would be a fraction. Okay. So for number 3, it's compressed vertically. So this is outside. By a scale, this was supposed to say not compressed, but stretched vertically by a scale of 4. So that means we're multiplying by 4, where A is 4. And then it's reflected over the y-axis. Over the y-axis is going to be horizontal, so that's going to be inside. So this function is going to be f of x equals, the stretch outside would be times 4 times the absolute value of, we have it reflected over the y-axis, so that would be a negative x on the inside. For number 4, stretch vertically, so these were switched. This is compressed. So vertically is outside by a scale of 1/2, so A equals 1/2. And it's translated up 14 units. Well, up is also outside, and we'd be adding 14. So that means there should be nothing on the inside of this one. We have f of x equals, on the outside we have our 1/2. On the inside we have the absolute value of x, and on the outside we have plus 14. You have time now to go and practice. Please let me know if you have any questions, need any help with anything from this.